I think my voice is very loud, but I don't know if online people can hear me. So we are interested in bifurcations. So these are qualitative changes in dynamics as some parameters of the system are changing, obviously. And this kind of changes can occur in a variety of systems on a variety of applications, including aerospace applications. For example, power grids were mentioned earlier today, but also other exciting systems such as ecological or epidemiological systems. In all of these, the issue of great importance is the ability to predict how far the system is from undergoing a bifurcation, to forecast that. So in particular, characterizing the nonlinear behavior near this stability boundary is very important, and determining the criticality of a bifurcation is very important. Is it catastrophic or not catastrophic? Maybe subcritical or supercritical. That can make a big difference in the way you approach that system. And then, of course, the reason why we study this is because we want to be able to predict and design the dynamics. There are, of course, methods to do this. In particular, traditional analytical methods have been most successful over many years. However, they require knowledge of the governing equations, as we were talking about earlier, or as Nathan was presenting earlier. The idea of governing equations might be changing. The nonlinear analysis of these equations might be quite complex or computationally expensive. And also models that we use, especially in real world applications, can be very large. So we deal with a lot and have inaccuracies as well. So we deal with a lot of issues. And the question that emerges is, can data-driven approaches address some of these challenges? So of course you might say, well, sure, there are data-driven approaches. They typically focus on a single parameter regime. They typically do not result in explicit parameterization of bifurcations, with a few exceptions that we've seen this morning. And what I'm going to talk about has a lot of similarity with that. But they also require extensive amounts of data. So what I would like to contrast are the two elements. One is model-based and one is data-driven. So I think what we can gain the most, in particular in understanding bifurcation phenomena, is if we combine the two. If we have a mechanistic, if you will, data-driven method, that is a data-driven method that is infused with the fact that there are certain invariants of the dynamics in the bifurcation. Therefore, these data-driven methods can be more accurate, not require as much data, but not be inaccurate and costly or large as in the models. So in particular, what can we infuse are these generic features that are associated with bifurcations, and then they can be incorporated in these data-driven methods. So the question is, how can we do this? Well, in bifurcations in particular, for certain classes of bifurcations, it's very useful to think of a center manifold perspective, right? And we understand that normal forms exist for many nonlinear dynamical systems. So when we, first class in nonlinear dynamics is studying normal forms. Why? Because they capture what is happening, and yet it's a very simple expression, right? So that's what we want to do. We want to use that and merge that, the fact that a normal form for that system might exist, with a data-driven approach. So for example, of course, a low-dimensional invariant manifold, which is essential to dynamics in the neighborhood of the critical point, can be determined through central manifold analysis. And basically what it says is that if you have a flow, x dot is equal f of x and mu, where mu is a parameter, you can essentially know its topology by doing a coordinate transformation from x to u, v, and w, u being in the centered space, v being in the stable space, and w being in the unstable space. And this trick that is used for the parameter variation being equal to 0 is to extend this to include the parameter in the analysis to get a model near the bifurcation point. So then the challenge becomes how to systematically or how to obtain these nonlinear transformations from x to u, v, and w, right? Especially if we would like this equation in u to be in its normal form, so in its simplest form. So then the question is, how do we find these transformations? We know they exist, but those might be very difficult to compute. And that's where we want to use data-driven methods. Okay, so now to get to the point of the structure of the architecture that we use, let me just further detail a little bit about this center manifold approach. So let me just, for simplicity, group the stable and unstable directions all in this x2. It's the thing where linearity determines the topology. And just leave x1 as the interesting variable. And of course, you can write these equations the same way. A and B are matrices with eigenvalues with 0 real parts, A, and with non-zero real parts for B. So, of course, the center manifold approximation tells us that there is a function g that relates x1, well, that expresses x2 as a function of x1. In other words, knowing what happens in x1, you will know what happens in the other dimensions of the system, right? This is a standard stuff for center manifold analysis. So if I want to write the dynamics on the center manifold, I have y2 is this variable that is in the sort of the boring space, if you will. And the reason why I changed from x to y is because now I'm also doing a transformation of these equations, so lambda is diagonal. Or bidiagonal. The other approximation, or the other transformation here, x1 is not made. I just substituted x2 with g. And so we have this reduced dominant vector field. We have the off manifold dynamics, that is this y2. And then we have, of course, this equation that it has to do with the fact that we have a parameter. So is the extended center manifold analysis that we are doing. So notice that I'm not throwing out this, this part of the dynamics, although it's just there along for the ride. But we will see later on why we cannot just ignore it, right? We need to include it in the analysis. Now, another thing I wanted to point out is that in order to come up with a normal form, formally, we make two more transformations. We know that from this equation, we can go to the normal form through a sequence of near identity transformations. So there are algorithms to calculate these near identity transformations. I'm just writing them generically here, so you know that these transformations exist, but I'm not going to attempt to find them. And then at the end, the other modification that I make, this last transformation from, so one was x1 to x1 tilde, and one from x1 tilde to x1. This last transformation is done such that I have a normal form where the coefficient of the dominant nonlinearity is 1. In other words, if I were to study a pitchfork bifurcation, I would have a 1 in front of the y cube. Clearly, I have a 1 or a minus 1 in front of y1 square, or a plus 1 if I have a fold. So therefore, the coefficient, whatever multiplies as the linear term, becomes a function of mu. Is not exactly, mu is not 1 or anything like that, is a function of mu. Now, of course, if I want to study this for a single dimensional bifurcation, then of course this h is a scalar function. So everything becomes very, very simple if we are available, if these transformations were available to the normal form, right? The normal form we all understand very well. So the question is how to perform this analysis, all these transformations for large dimensional systems or for models that are inaccurate. That becomes a big challenge. If you have these transformations, great. But if you don't have them, then how do you find them? And that's where we are using data-driven methods to get there. So basically, I'm going to explain this architecture in more detail, but it's an autoencoder like what you've seen discussed yesterday, and also a lot of this was discussed today, with a couple of exceptions. First, you notice here that we have the sort of the normal form is present, and we also have some of the other dimensions that are involved. This contains three components. The encoder is a nonlinear transformation to the center manifold. Inside here, we use a normal form for the dynamics in the center block, or this recursive center manifold block. And then on the other end, we have the parameter-dependent decoder. We also notice that we have x, which is the state, but we also have the parameter. And there are two transformations. Of course, the transformation for x to y depends on mu, as we've seen in all the transformations we had before. Mu was present everywhere. But in addition to that, we have the transformation from mu to beta of mu, which is the coefficient of that linear term, if you will, in the normal form. So those are ingredients to the center manifold recursive block. And then this block will predict the dynamics at some time index t plus L later than time index t. And then the decoder will transform the nonlinear, will be the nonlinear transformation to the observation space. So now let's look at these three components of the architecture separately. N11 that is here is basically simultaneously performing the nonlinear center manifold approximation and the normal form transformation. So it's all of them are on the shoulders N11. This is a function of not just x, but also mu, because we're using this extended perspective where we have mu dot equals 0 as one of the equations. The other part here, N12, is the mapping the physical parameter to something that we like that we call effective bifurcation parameter, right? Mu is the usual bifurcation parameter, but once you make this transformation the normal form, then we have this beta mu is the coefficient that varies there. So it's a very simple bifurcation once you are in the normal form, but the coefficient is more complicated function of your original beta. Then if I look in the middle part, this is the recursive block for the center manifold. This applies a constraint on the latest space dynamics. So very much like what we've seen earlier today, it's not just free to be whatever we want, but it's something that has a specific functional form. And why? That's where I call it mechanistic, or there where the physics come in. We are forcing the system to have this specific normal form, and therefore we are basically informing the data-driven method as what are the underlying dynamics that we want to capture. This block forwards the reduced dynamics in time according to this normal form of the bifurcation. In other words, it integrates y and gets from y of t to y of t plus L. Of course, it also does that not just for the y1, but for all the other y's that we are concluding. What this block, by training this algorithm, what we're doing, we're essentially searching to find the best normal form that fits the data while optimizing its parameters. So you don't know which normal form will fit the data that you have, but you try several of the standard normal forms and you'll see which one fits the data. In other words, or as an example, if I were to consider H to be beta y1 plus some sort of weight value here, W, if it turns out to be +1, it is subcritical. If it's -1, it will be supercritical. And that's what we want to know at the end. All right, and then finally, the last thing I wanted to mention about this block is the fact that these variables are not trivial and they have to be here. This is because the transient dynamics is present in the data, and the data is off the manifold, right? So if you have experimental data that will be just on the manifold, then you wouldn't need these equations, obviously. But there's no way to know that the data points that you have are not just on that manifold. So because of that, they must be included in the analysis. And then finally, the third block on the right, the decoder component, transforms the latent space dynamics back to the observation coordinates. And one interesting thing to note here in this sub-block, if you will, N21, if we set beta of mu equal to 0, and we set all the y variables corresponding to these states, let me go back a little bit, to these states that I mentioned that must be included at the training stage. If we set them all to 0 as inputs, then basically this relationship from varying y, we would get x. That will give us the center manifold of the dynamics. So the center manifold is kind of built in this N21 with specific inputs. All right. Now, this looks great. We'll just put everything on the shoulders of the training algorithm. But in order to get proper answers, we have to have the right type of loss functions or losses to train the algorithm. And we define 3 losses. The first is the autoencoder loss, the traditional thing that is that if you have x input, you go to latent space, you get x back. So that is the loss function says basically that mu output is equal to mu input and x output is equal to x input. In terms of the blocks N1 and N2 and their components N11, N12, and N2, well, N21, N11, and N22, this is the expression that you have here. A second level of or second component of the loss is the state prediction loss. This is basically saying that we are predicting not just from x of t to x bar of t, but x of t plus L. So basically what we are enforcing is that the output be exactly the input that happened later, right, in the sequence. So this basically ensures predictability of the output in the physical space. And then, of course, in terms of the blocks involved, they are shown here. Some details I'm going to omit. Finally, the third component of the loss is enforcing sequentiality. So basically what we want to guarantee is that the coordinates in the latent space, the y, can predict the x at later times. So therefore, we want essentially to say that y at time tk plus L matches what y will be later on. So this is the last component of the loss, and of course these are functions of n1 and NCM, and they are of course functions of the inputs that we have as measured data. So in summary, the loss has three components, as I mentioned. This one, the autoencoder, this one that says that it's predictable, this one that predicts the states at a later time, and this one that ensures that the latent space can predict future states in physical coordinates. There's one other detail to this loss, which is the fact that you see x are in same coordinates. So these are in some, if you will, units. And this one is in the latent space and might have quite different scaling. So this gamma is a coefficient that we apply to scale losses so they are in similar order of magnitude. So with this, I would like to go and explain a couple of examples of applying this approach. So first, we consider this Lorentz equation. Seems to be a very nice equation. People look in this and in this kind of analysis. And one of the reasons for us why we chose it is because there are explicit approximations to the centerfold dynamics. This y dot, y2, and y3 dots. We have a formal expression. So I wanted to see exactly this is what we expect beta to mu, the fact that it's going to be -1 that weight. And not only that, but we have the approximation of the center manifold itself. So if we predict what the center manifold is, then we can verify that whatever the network predicts is what the analytical analysis predicts as well. So with that, we train this Lorentz equation for certain parameter values, this 0.25 and this 4. Mu is the bifurcation parameter. We sample data, we constructed trajectories, and then we sample just pairs of data at time t and t plus L from the measured data. There were 5,000 data points here. And we trained these algorithms. Of course, there are many more details there in this paper cited on the bottom. The question after the training is, what is H, what is beta, and what are these lambda i's? That's what we would like to know. So first, this is the Lorentz equation, as I mentioned, with these coefficients. These are the values that were identified in terms of the transformation. So there's a -1 in here, beta of mu 0.23 instead of 0.25, and 4.14 instead of 5. So there are approximations, but are good approximations. And most importantly for us, the fact that this is a supercritical pitch for bifurcation was identified correctly. That's very important. And also the fact that beta as a function of mu was identified reasonably accurately. That means that we have confidence, we understand if we study the bifurcation in the latent space, we will know what happens with the bifurcation in the physical space, right? If we don't know how to go from mu to beta of mu, then we operate with this beta mu, we don't know what actually it is. So that is important. Not only that, but we compared the center manifold itself. So as I said, if we input the two states that are stable, in this case are both stable, to 0 and a small value of beta here, then we get an x, and then we can plot x1, x2, x3, the three outputs, and we plot the identified center manifold versus the reference, which is obtained through analytical expressions, right? And so, so basically, these are projections of the two spaces to see that the approximation is fairly accurate. But then we said, well, but this is a low dimensional system. can we make it more complicated, right? Can we enhance the complexity? Now, how can we enhance it? We use the technique that one of the previous speakers used as well today. Basically, we define these 4 equations, which we kind of came up with. These have at mu equals 0, there's a bifurcation, and the eigenvalues are 1 is 0, 1 is -2. The other 2 equations have constant eigenvalues that don't depend on mu. And you say, well, this is also low dimensional. Yes, it is, but then what we did is we constructed a 100-dimensional space by essentially expanding from these z's to x's, with P1 and so forth, P6 being Legendre polynomials. And so in the end, we have a large dimensional input that is 100 dimensions this time, and we are applying the same kind of procedure. Now, when we do this, however, we didn't want to have 100 or 99 dimensions in here. And instead, we said, well, we want to limit this NL, the size of this subspace that we are using here. And so how to do that? Well, we use the classical technique, which is basically whenever you don't know what's the dimensionality of data, you do a POD, and it gives you a rough idea of what you might be dealing with if the system were linear. Of course, it's not, but for the linear part, might as well look at that. So what we did here, we pretended we did not know that this was 4-dimensional. We said, give us this 100 dimensions. Let's do a POD and let's see how many dominant values we have from POD, and they came out that it's 4. Not surprisingly, obviously, we built it with 4. And so therefore, we use this NL equal 4 in here and run the identification. So when we ran the identification, these are the results. This is the reference dynamics, and this is the identified dynamics with the latent space NL of dimension 4. So when we do that, you again notice that we get the right bifurcation type. We have approximately the coefficients that we need to have, and also the beta as a function of mu comes out pretty accurate. So this was encouraging that, limiting that NL to 4 is a good idea. But then we said, well, what if you make a mistake there and you pick the wrong ML? Is that important? Yeah, it's very important. In particular, if you ignore it, because some people like to ignore that, and say, well, I'm just interested in what happens on the center manifold, forget about all the other dimensions. The problem is the data that you feed into the training algorithm is not on the center manifold, right? So if you do that, you are training to the wrong thing, right? The data is sort of incompatible. So if we did that, we put NL dimension 1, meaning we completely removed all the other things, right? It's just Y1 dot and beta dot equals 0. And so on our test data set, we had 3 orders of magnitude increase in the error. We converged to a value that is not very small. In other words, the training was not very good. And not only that, but when we looked at what is the prediction, it was completely off. So again, the black line is the sort of theoretical analysis. The blue is the approximation with NL equal 4. And the red is when we ignore the other dimensions. So obviously, ignoring those dimensions can create a problem because, again, you're training to the wrong data set. If you could have the perfect data, then you wouldn't need that. But you don't have the perfect data. And the reason why we are interested in this and the larger dynamical systems is because we wanted to look at predicting critical transitions and bifurcation diagrams from safe measurements. So what does that mean? It means imagine you have some sort of equilibrium state of a system and some parameter. As you change the parameter, you might have some bifurcations. Well, what we want to do is, by knowing responses of the system in the pre-bifurcation regime, predict that there might be a bifurcation at A or at B. That has implications in, for example, ecological systems to predict emergence or extinction. It might have implications in disease dynamics for predicting outbreaks and things like that. So we are interested in this, and also in aeroelastic systems predicting flutter and so forth. So we've been working on this for quite a while. So we do this by this method that I call forecasting. Of course, forecasting, bifurcation forecasting, I should be more specific, by using the rate of recovery from perturbation. So if you look at how fast the system recovers, when the system is in the vicinity of a future bifurcation, it slows down. For a category of problems that is critical slowing down, that is a known phenomenon. And so we're using this kind of recovery rate as a function of time to understand where the bifurcation is. And based on these kind of recovery rates versus time at different parameter values, we can predict the bifurcation diagram. So where is this the combination between what I just described with the normal form analysis and the forecasting? Where do they come together? Well, they come together because forecasting what happens in this simple normal form is really very easy. So if we had this available from data, then we will be able to say what are the recovery rates in the Y, and what is the bifurcation diagram well, what is the Y versus mu, or recovery rates versus the bifurcation parameter diagram, and then converting it back to physical, we will be able to predict the bifurcation diagram. So basically what we do is we need to identify the rates on the manifold, and therefore we need to know that manifold. We need to approximate rates, but we can't do it with observations that are on the manifold only, because we don't have those observations. And then the sampling is sparse and random, and that affects the way you approximate recovery rates. So if you only have data that are spread around, you cannot make a clean, nice plot of recovery versus time. You only have a few points there. So you cannot even do finite differencing sometimes. So the idea here is to use this transformation, which can be done with not so well organized data inputs for X, and then forecast in the latent space and then expand it back to the physical space. And we did that. I'm showing some results here, a very simple results, a very simple dynamical system. And again, we expanded this in a 20-dimensional space, and I'm plotting one of the states x5 versus mu, and this is the reference bifurcation diagram and the forecasted. And the reason why I'm showing this plot is to see that this bifurcation diagram can be quite complicated. The actual dependence of the physical variable onto the bifurcation parameters can be quite okay, so this shows to it can be quite complicated, as is shown here, right? I mean, you have two x's for two different mu's, etc. So it's a complicated diagram. So in summary, what I hope I convinced you of is that you can use deep learning for bifurcation analysis. This is rooted in central manifold theory, meaning we enforce that mechanistic aspect, the normal form in the latent space. That is really the big advantage. We identified the bifurcation time and its parametric normal form on the central manifold. And this has important advantages for data-driven analysis of the stability, as well as order reduction when we have limited information regarding the low-dimensional dynamics that is available. So with that, I would like to thank you for, again, Bogdan, for inviting me, and you for attending the presentation. If I can answer any questions you might have.